The second fundamental theorem of calculus. If f is a continuous function on an open interval I containing a, then for every x in the interval, the derivative with respect to x of the integral from a to x, f of t dt, is exactly f of x. Now, this could be somewhat misleading. Basically, what it is saying is that the derivative of the integral, since the integral is already the antiderivative, so the derivative of the antiderivative gives us the function evaluated at the variable x, f of x. Now, it's misleading if x is a function of x, such that if this term appears x squared, or if it's cosine x, then the result becomes f of x times the derivative of this term here. There is one problem where we run into that, and I will show you. Let's look at some problems. I think it's very straightforward. Here in this exercise 75, integrate to find f, capital F, as a function of x. And then part B, demonstrate the second fundamental theorem of calculus by differentiating the result in part A. So here, just find capital F. That is, just integrate. So we integrate here, we get t squared over 2 plus 2t, evaluated from 0 to x. And so that gives us x squared over 2 plus 2x. The evaluation at 0 just yields 0. This is part A. So here, part A, capital F of x is equal to x squared over 2 plus 2x. And then it says for part B, demonstrate the second fundamental theorem of calculus by differentiating the result here. So we find f prime of x. And so we get the derivative of x squared over 2 plus 2x. So this gives us 2x over 2 plus 2, which is x plus 2, which is represented by that term there. Well, that's it. What the fundamental theorem of calculus says, the second fundamental theorem says that capital F prime of x is equal to t plus 2 evaluated here at x, which just becomes x plus 2. So instead of taking the integral and then differentiating, we use the second fundamental theorem that gives us the result directly, that the derivative and the antiderivative, they're inverses, and so they cancel out. So you have left is the function evaluated at the top or the last limit of integration. Here, just simply use the second fundamental theorem of calculus to find f prime of x. So f prime of x is t cosine t evaluated at x. This is just x cosine x. So what about this one? This one would take some work on this, because notice that the lower limit of integration is a variable and not a number, such as a or 0. So because of that, we have to make it match up to the theorem. So we can write this as the integral from x to 0 of 4t plus 1 dt. This is plus the integral from 0 to x plus 2 of 4t plus 1 dt. Well, this integration is swapped, so this is negative times the integral from 0 to x, we have that property of 4t plus 1 dt. And we can do the work over here, but let's just go ahead and just repeat it to be consistent with the first integral. Okay, so if that be the case, then f prime of x is equal to, here's this negative, and this, it's not absolute value, it's negative. This is 4, the t is evaluated at x, so this becomes 4x plus 1. That's the first one. Then plus, this is, I better use bracket there. This is a bracket 4, and this t becomes the x plus 2, or the evaluation there, according to the second fundamental theorem. And so now all we're doing is simplifying. This is negative 4x minus 1 plus 4x plus 8 plus 1. And so they cancel. And we have left 8. What about this one? This was the one, if you look at the theorem, is the derivative of the integral from a to x. But here, this top integrand, limit of integration, is a function of x. So f prime of x becomes this square root of t, which is the square root of sine x, and this dt gives us its derivative. That is, that this becomes the derivative with respect to x of that variable up top. So this becomes cosine x times the square root of sine x. And you only do that when that top integral, in dealing with the derivative of the integral, when that top integral is a function of x, then we have to actually compute its derivative as well. So basically all we've done was to apply the so-called chain rule. Well, that'll do it for now. Thank you.